Good morning, good afternoon, good evening, wherever you are, and welcome along to the AMETEK Solid-State Controls webinar for October. And this month we're talking about batteries, stationary batteries, battery myths, and various battery topics. As always, can you please let me know in the chat bar that you can hear me okay? That would be appreciated. And I'll just leave it for a few moments for everybody to come in the room. Good stuff. Thank you for letting me know that you can hear me. So that is good. So while we're waiting for everybody else to join, I'll go through a few introductions. First of all, my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls, and I'm based out of the Stafford office, which is southwest of Houston in Texas. And we are we're having a cold front come through just now, so there is a lot of thunder and lightning going on. Hopefully that will not interfere with this presentation today, but I'm looking forward to the cold front after it comes through, that's for sure. I have 20 years experience in the industrial UPS industry. As you can tell from my accent, I'm not from round these parts. I'm from Scotland originally, and I used to work in the North Sea on oil platforms, maintaining, installing, and repairing UPSs. I've worked with all the major UPS charger manufacturers. Regarding the webinar, there will be a lag of around about 30 seconds from when you hear my voice to when anybody types something in the chat bar. Basically, Webinar Jam, which is a platform that we use, it's got to convert this broadcast into iOS device, Microsoft device, and Android device. So there's obviously some processing time that is required for that. So from when I speak to actually when you hear me speak, there's about a 30-second delay. So I'm not going to see your comments until 30 seconds after I've said something, if that makes sense. Webinar Jam has a panic button. All that means is, for me, if I start to see comments that you can't hear me, you can't see something, that something has gone wrong with the webinar, then I can press the panic button. That will start a whole brand new webinar and invite everybody into that room again. And we can carry on from where we left off. A very popular question that we get is, will the webinar be recorded? And yes, the webinar will be recorded. Immediately after the webinar is finished, you should have a link where you can go into Webinar Jam and you can re-watch the webinar at your leisure. But the problem with that is it treats it as a brand new webinar. So when you press start, you can't fast forward it, you can't rewind it, you can't move through the presentation like you would if it was a video. Basically, you press start and you've got to watch the whole thing all over again. So our fantastic marketing department, after the webinar is finished, will download the video, convert it to an MP4, and then it will be uploaded to our YouTube channel tomorrow. So if you do want to watch it again, there was some interesting stuff that you want to recap, then wait until our fantastic marketing department upload it to our YouTube channel. And as always, the webinar should last around about an hour, but that obviously depends on A, how much I speak, and sometimes I do go off on tangents, and B, how many questions we get. And also remember, you can type in questions at any time during the presentation. I probably won't answer them as we go through. I try and leave the questions, the Q&A, until right at the end of the webinar. But if something comes up that I see that is pertinent to what I'm talking about at the time, I will try and take the time to answer it. So it looks like everybody pretty much is here. So today we are going to speak about batteries. Now, please do remember, I am a UPS expert. I am by no means a battery expert. You know, there's always a battery connected to a UPS, so I do know a lot about batteries, but I am in no way an expert. So please bear that in mind. So we're not going to go into really deep technical things about the batteries, like the chemical reaction, how the battery produces power or anything like that. It's just going to be some good information that you can take away and put into action. Okay, so we're going to understand the basics of the lead acid battery, understand the purpose of a battery in a backup power system. We're going to go over battery sizing, and we're going to discuss some common maintenance mistakes, and we are going to discuss some common myths about batteries. Now, before we go any further, I would like to tell everybody that we're going to be focusing mainly on lead acid, because that is the technology that is mostly used in standby power operations. We'll touch on NiCads a little bit, and there is a mention of lithium ion, but I do not go into really anything about lithium ion in this presentation today. It's out with my skill set at this time. So the first thing is we're going to go over terminology. So the first things first is what you see on the screen here is what we call a cell. It's an electrochemical cell, and this is a lead acid cell. So you can see here on the left-hand side, we have the what they call the anode, or the positive plate, which is lead dioxide. And then on the right-hand side, we have the cathode, which is the negative plate, which is usually lead, pure lead, or an alloy combined with lead. They are dipped into a liquid, which is H2SO4, which is sulfuric acid. And the combination of the lead dioxide, the lead, and the electrolyte generates electricity. And in a lead acid cell, that is a nominal 2 volts. Okay. Now, before we go any further, although this is a cell, please do bear in mind that you can connect cells in parallel. So excuse my drawing, but in this one here, okay, we have 2 positive plates and 2 negative plates now, but it's still classified as a cell, and it will still generate 2 volts. And in truth, you can have up to 17 plates, 17 negative plates and 17 positive plates inside one jar, which is what we're going to go into in a moment. But this is the basics. This is a cell. Okay, so the question is then, what is this? Now, what we call this in the battery industry is a jar. Okay, this jar has 3 cells in it. So the jar is the actual container, and this has 3 cells in it. How do I know it's got 3 cells? Well, we have one positive post there, we have another positive post there, and we have another positive post there. And I can see actually from the side of this jar that there is 3 divisions. This is actually a plastic divider that goes in between the cells. And we can see that we have 1 cell, 2 cell, and 3 cells in this jar. Okay, and if you look really closely, you'll actually see that this gray plate here, this is a negative plate, this black plate here is positive, there's a negative plate in here, there is a positive plate here, and then there's a negative plate here. Okay, so this has 2 positive plates and 3 negative plates inside one cell. Okay, so that's a jar that has 3 cells inside of it. And then this is what we would call a battery, or a battery string. Is when you connect multiple jars in series to connect to a system. So in this one here, we have 6 on the top here. You can see we've got 6 here, and on the bottom we've got 6. So this is a 12 jar battery. Okay, so 12 jars. Now remember, each cell is 2 volts because it's a lead acid battery. So that would make this a 24 volt DC battery. Okay, hopefully that makes sense. Now it does get a little bit confusing sometimes, because obviously, as I've mentioned here, this is the looking front on this battery. I can see that there is 2 positive posts here. So I know that there is only 1 cell in this battery, but this cell contains 1, 2, 3, 4, 5, 6, 7 positive plates, and it's going to have 8 negative plates. So that this is still classed as 1 cell in 1 jar. I hope that makes sense. So when it comes to lead acid, there are 2 main types. On the left-hand side here, you can see we have vented lead acid, or VLA, and these yellow plugs here, these are actually shipping plugs. When you install these batteries, you should remove these shipping plugs, and then you will put in a flame arrestor, which kind of looks like that, into the place where the vent plug is. So these are called vented because the gas is supposed to, when it's charging and discharging, it will vent some gas into the atmosphere. Now, on the right-hand side here, we have 4 different types of valve-regulated lead-acid batteries, or VRLA. So this one here is a 12-volt monoblock, or a 12-volt jar. Okay, it actually internally, and you might be able to see at the top there, we actually have 1, 2, 3, 4, 5, 6 vents there. They are recombination valves, and they're there if there's too much pressure within the battery to allow some of the gas to get out to stop the battery from swelling. But there is 6 cells within this 12-volt jar, and we've got 1 positive post here and 1 negative post here. And that's the same down here, but this one here, rather than have the terminals on the top, the terminals here are called front terminals. So you connect to the front of this 12-volt jar. Now this battery here, this is called a stackable valve-regulated battery, and each of these jars contains 1 cell. In truth, the 2 positive plates here are connected internally on this this type of jar here. So this is actually 1 cell in a jar. So that's a 2-volt block. So if we count here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 batteries here. So that is a 24-volt battery string connected together. Okay, hopefully that makes sense. And at the bottom here, there's another example of another 2-volt stackable monoblock or jar. It's standing upright this time, but these are the positive terminals, these are the negative terminals, and once again, these are connected together internally inside the battery. Okay, so this is still a 2-volt monoblock, even though it has 3 positive terminals and 3 negative terminals. Okay. So a thing that confuses a lot of people is voltages of cells or batteries. So cells are always listed at nominal voltage, and nominal voltage is what the industry has decided is pretty much I wouldn't say it's the open cell voltage of a battery. It's just the amount of power the industry decided that each type of cell will generate. So for a lead acid cell, they say the nominal voltage is 2 volts per cell. Okay. For NiCad, it is 1.2 volts per cell. Now for lithium, it's a little bit different because of the different technologies that you can get. The nominal voltage can be a little bit less than 3.6, or it can be a bit more than 3.6. You must check the data sheet for lithium ion, but it's usually round about 3.6 volts is a good starting point for the nominal voltage of a lithium ion cell. Okay. Now, in the industrial UPS and switchgear world, the majority of batteries contain 60 cells of lead-acid batteries. So that is a nominal string voltage of 120 volts, because that's 60 times 2 volts, which is equal to 120 volts. Now, for NiCads, they usually use 96 cells. That actually gives you a nominal voltage of 115.2. Some people will still refer to this as a 120 volt DC string. Okay. But you've also got to understand that the only thing that drives these voltage selections is the tolerance of the load circuits that they supply. And we'll go into that in a little bit. Now, obviously, there's other voltages that you can use in telecoms. 48 volts is very popular. There are a lot of 240 volt DC UPS systems, and in the commercial world, there is a lot of 480 volt DC systems in UPSs. And also for some situations, there are 24 volt DC systems as well. But for the majority of work in the petrochemical industry, the power generation industry, we're looking at either 60 cells or 120 cells. So, as I said, the load circuit tolerances are what drives the selection of batteries. So for a 60-cell lead-acid system, the float voltage is around about 135 volts approximately, and we'll go into that in just a moment. But most people recognize that it's 2.25 volts per cell. That is the float charge required for a lead-acid battery, roughly. Okay, and 2.25 times 60 is equal to 135. Okay, now for a vented lead acid system, you have to be able to put that system into equalize, and the equalized voltage is generally taken as 2.33 volts per cell, and if you times 2.33 times 60, you get a voltage of 139.8 volts. And then in the design of your system, there has to be an end of discharge voltage, because there is a point where you don't want to discharge a lead acid battery past. And once again, in the industrial world, that's usually taken as 1.75 volts per cell. So if you multiply your 60 cell system times 1.75, then you will get 105 volts DC. So these calculations tell us that the DC voltage range that the loads that this battery should be able to work at is anywhere between 105 to 140 volts DC. Okay. So if you say this is connected to a switchgear system, then the relays and all the associated parts of your switchgear system must be able to handle between 105 volts and 140 volts DC. And in truth, that should be the case because it's an industry standard. Okay, so this picture here, this shows you a cutaway of inside a 12 volt jar or a 12 volt monoblock, basically similar to a battery that you have in your car. So on this one here, we have the negative post. So that's the negative post here. How do I know it's a negative post? Because the negative strap, this one here, is connected. So I know that is the negative post. So that means this post here is the positive. Okay. You can see the negative plate. So this is the negative plate here. And then there is a separator. It's like a rubberized material that isn't affected by the acid inside the cell. And it separates, physically separates the positive plate, which is here, from the negative plate, because obviously the positive plate and the negative plate can't touch each other, because then there would be a short. Okay, so the separator has to be thin enough because you want the two plates to be as close to each other as possible so the energy transfer can take place. And then, as you can see, the positive plate goes up onto what's called the intercell connector, and that will connect to the negative plate of the next battery, and then the positive will connect to the negative, and then it will go like that, and then out to the positive post there. Okay. And then obviously in each, you can see it here, there is a line in between, and that is a partition. That actually completely separates each of the cells from each other. Okay. And here's a good side picture of a cell in an industrial battery, one that you can actually see inside. You can see our electrolyte level is there. So basically, if I draw a line across here, this is all filled with electrolyte, okay, sulfuric acid. Now you can see here, I know that the positive plate, you can always tell the positive plate goes down here because this is a darker chocolate, kind of black color, okay? And that's connected to all of the black plates, and they're connected in parallel, okay? And then you can see that yellow thing here, that's a separator. The gray plates are the negative plates, okay? And then you can see on this cell here, so once again, this is the positive. So this one here, we get to see the negative side. So we can see that this connector here, which is connected up to these negative terminals, it's a gray color. And that's where all the gray negative plates are connected to, once again, in parallel. Okay? And it just repeats all the way throughout the battery. So that's the inside of a battery. Obviously, with a vented lead acid battery, you want to keep the electrolyte level somewhere between these two lines here, okay? I wouldn't get obsessive about it. You know, it's okay to let the electrolyte level get to the low level line here, because basically, as long as we don't expose these plates, we're going to be okay. So if it does get to the lower level line, put it in your maintenance system to top it up as soon as possible. But you don't have to panic about it. Okay. So we're going to talk about charging now. So here's a typical charging system. You've got your MCC here, usually supplying 480 volts into your charger. Your charger converts that into a voltage. It's a nominal 120 volts DC for this one if it's a 60 cell system. That goes out to our DC panel and feeds all of our load circuits. And then down at the bottom here, we have our battery connected in parallel. Now, remember, I said it's a nominal 120 volts, but we have to charge it at the battery manufacturer's recommended amount, which is 2.25 volts per cell. So the voltage is going to be approximately 135 volts DC. And there's a reason why I say approximately, okay? It's because each battery manufacturer has a different level that they want their batteries to be charged at. So this table here is from an Enesys manual, and they give you two different float voltages, and it's based on the specific gravity of the electrolyte in their battery. You can buy a low specific gravity battery, which is 1.215 specific gravity, or a high specific gravity battery, which is 1.25. And that's basically the nominal specific gravity is higher on this one here because they have more sulfuric acid in the electrolyte solution than they do on this one here. So this one here will actually give you more power than this one here, okay? But that changes what the system needs to be charged at. And just to confuse things even more, the makeup of the plate inside the cell, because they're not all pure lead, there's usually a frame, and the alloy of the frame of the battery could be antimony or it could be calcium, and that affects the float voltage as well. So if you have a 1.25 antimony battery, they're saying you need to charge it between 2.17 and 2.21 volts per cell. So if you take the halfway point, that's going to be approximately 2.19 volts per cell. Now remember, before I go any further, this is all at 77 degrees Fahrenheit. All the US manufacturers quote their charging rates at 77 degrees Fahrenheit. Okay. Now let's look at the lowest specific gravity, the 1.215 specific gravity, and we'll do the calcium one. It says between 2.17 and 2.26. So that's a spread of 9. So that's about 5 volts. So there, roughly, you should be charging those at 2.22 volts per cell. But this one here is the most popular, is where we get the 2.25 volts from. And that is a 1.25 volt specific gravity with calcium plate grid. And that works out, the average in the middle is 2.25 volts per cell. Now remember, that's for Enesis. Okay. Here's the table for C and D. Their recommended float voltages, I've highlighted it here, is between 2.2 to 2.25 volts per cell for a calcium plate. So that would be a 2.23 volts per cell charge voltage at 77 degrees Fahrenheit. Okay. And if it's an antimony cell, they're saying that's 2.15 to 2.28. That's a spread of 13. So let's add 7 onto 2.15. So that's going to be a 2.22 volt per cell for the antimony. Okay. Hopefully that makes sense. And I've picked one other manufacturer just to throw it in there. They're actually a lot easier. They're saying, look, here's our type of cell, and here is the float voltage. And in truth, the float voltage is the same for every cell except for this one here. The grid power OSP.XC from Hoppeky is 2.25 volts per cell, and all the others are 2.23 volts per cell. Okay. Now remember, for your string voltage, you have to multiply that by 60 if you have 60 cells. So that would be 60 times 2.23, which is equal to, I can't remember, I think it's about 132.8, something like that. I can't remember exactly. Okay, so why do we even need to use batteries? It's a simple question. It's because Westinghouse and Tesla won. Unfortunately, we don't use DC in our transmission systems. We use AC, and we use big turbines to create the AC in our power generation systems. And the problem is, I know it sounds simple, but you can't store AC. And if any of you have figured out how to store AC, please let me know, because I'm going to make an absolute ton of money from your idea. You just can't store AC. That's why we have to use batteries. If we went to a DC grid, which is possible these days, the technology is out there to have, instead of having transformers. The reason we use AC for the grid is because it's easy for us to step up the voltage to transmit at high voltage, low current, so there's less losses. And then we can use transformers to step that down to supply factories and houses. When DC was first idealized as being used in a transmission system, there was no easy way to generate a high DC voltage to transmit it across the power lines with low current, and then step that high voltage DC down to suitable voltages for household use or factory use. But now the technology that is used in DC to DC converters, it actually would be possible to switch to a DC grid system at this point. But I think we're too far down the line to go there. So we have to have batteries because the grid is good, but there's always going to be outages. And Texas was a perfect example of that when we had the freeze in, was it January, February of this year? We had a huge amount of power outages. So that is why batteries are used, is to store power when the power is good. And then when the power goes out, the battery then supplies that power to your load circuits. So you can shut them down in a controlled manner, or you can ride out the outage until the power comes back on again. So in this drawing here, this goes back to a typical charger DC system. We've got our AC going in here. This rectifier converts it to DC, and then that goes out to our DC panel. The only reason the battery is here is for storing the power if we have a failure on our AC input. Okay? In truth, don't ever do this, but you could run with this disconnect open and the battery disconnected, the AC getting converted to DC. It will feed the DC panel and it will keep your loads energized. But you need to have this battery backup if there is a power failure. And the same can be said for a UPS. This is a drawing from one of our AMETEK SCI manuals. We've got our AC input going in here. Then we convert AC to DC. Okay. And we've got our battery here. The charger is only there to supply power to keep the batteries charged, but the charger will supply power to the inverter, which converts the DC back into AC, and then that goes out to our critical loads out here. In truth, you can run our UPSs with the battery disconnect open, with no battery connected. It will run absolutely fine. It will supply your critical output loads. But if you have a power outage, then you're dead in the water. Okay, that's why the battery there is only to store power. So if you have an AC failure, you transfer to battery operation and you carry on supplying your critical load circuits. I see there's a couple of questions come in, so I will answer them when I get to the end. I'm not ignoring you, I promise. So now I'm going to discuss, what happened there? Hopefully everybody's still with me. We're going to discuss battery sizing. Let me clear that. And I'm only going to cover sizing for a UPS because obviously that's the world that I live in. So we'll discuss how you would go about sizing a battery for a particular UPS. So here is the rating plate for an AMETEK 10 kVA UPS. Okay. Now, if you go down to the DC input section here, it says that at full load, we're going to need 76.6 amps. Okay. So to get 10 kVA, we're going to need 76.6 amps. So if we go to the next slide, what I'm going to do is I'm going to take you, basically use a kVA rating to get you where you need to be. So a 10 kVA inverter with a 0.8 power factor can only produce 8 kilowatts of real power. Okay, that's the first thing a lot of people get confused about. You have to size it at the 8 kilowatts, not at the 10 kilowatts. Okay, we do sell systems that have a 10 kVA 10 kilowatt output, but in most systems they're rated at 0.8 power factor. And also remember, we don't live in a perfect world. Inverters are not 100% efficient. Okay, so for our inverters, for a DPP, which is our pulse width modulation inverter, it's round about an 88% efficiency rating. So we have to work backwards. So we're saying for an 8 kilowatt output on our inverter, if the inverter is 88% efficient, basically you divide 8 kilowatts by 0.88, that means we need 9.09 kilowatts of power on the DC side to produce 8 kilowatts of power on the AC side. Okay, now we need to know the DC side because that's where the battery is connected. So hopefully you can follow me through this. So that's the important number here, 9.09 kilowatts. So now that we know the kilowatts we need, it allows us to work out the DC current required for the battery at full load. And remember, we have to expect the battery to discharge down to 105 volts DC as an end voltage. So we use Ohm's law. Power is equal to volts times current. So current is equal to the power divided by the voltage. So current is 9.09 kilowatts divided by the end voltage of 105 volts. So we know our battery is going to have to supply 86.6 amps. Okay? That's how much the battery will need to supply to keep the inverter running at fully rated load to give you 8 kilowatts on the output of the inverter. So the next question we have to ask ourselves is, well, how long do we need it to operate? So that is decided by the load circuits and the safety requirements at the design stage. So if it's a DCS system, a distributed control system, most plants, they want that DCS system to run for about 3 hours. So what we're going to do is in this example, we're going to assume that the team calculated that we need 3 hours of runtime. Okay. Then the next question you have to ask yourself is, well, which manufacturer and battery type? And that is up to you as the end user. You can use price to make that choice. You can use what you're familiar with or what you think gives you the best life for your battery. These are all things that you have to look at as the end user. You've got to figure out which manufacturer and battery type you're going to use. So in this example, we are going to assume you had chosen an Enesis vented lead acid system. We've had previous good experience, let's say, with the DX range. So we would like to use the Enesis DX range again in this system that we are sizing. So now we know the current, we know how long we need that current for, and we know which battery we're going to use. So what we do is we go to the Enesis DX battery datasheet, and we go to this 3-hour column here. Okay, now remember, this is down to 1.75 volts per cell. This is the industry standard that we use. So this is the column that we're looking at. I'm terrible at drawing with this pen, but okay. So then we go to the left, we go to this column and say, okay, so in the previous slide, we said we needed 86.6 amps of current out of the battery for full load. Well, we can't use the DX5, this one here, because that's only going to give us 69 amps. But what we can use is the DX7, because it will give us 99 amps for 3 hours. So which is more than 86.6 amps. You could go to the DX9, any of the ones above the DX7 is going to work for you, but obviously the price goes up the more power you need. So the best solution for this 10 kVA UPS that has 8 kilowatts at 0.8 power factor, for us to have a battery that lasts 3 hours, our best solution is the DX7B. Okay, and that is how you size a battery. That's the manual way to do it. Okay, that's the hard way, as I put it on this slide here. Most of the battery manufacturers have a sizing tool that will allow you or a rep to use. And basically you can type up all the information. I did it for this battery here. I put in, it was a UPS down to 1.75 volts per cell. The load of the UPS was 10 kVA, but it had a power factor of 0.8 and an inverter efficiency of 0.88, and it calculated the load kilowatts required to be 9.09, just like I did in the manual. And it's saying here for the DX range, it says it's good, and it gives you a 20.3 margin. So you've got 20% more power than you actually need. If you wanted to use a single battery, probably the most cost-effective battery would be this ES09, but it only gives you a 9.4%. But it gives you a choice. You could even use 2 strings if you wanted to, 2 strings of CX09s. So each of the manufacturers will have a battery calculator that you can use. Okay, you just go to their websites, go to the Enesys website, and go to the C&D website, probably go to the Hoppeky website. You may have to sign up for the battery calculator, that put in your email and create an account, but it should be free, and it makes it easier for you. Okay. Now we're going to talk about some maintenance myths, I suppose. Okay. So let me just do something on my other screen to get me where I need to be so I can describe what's going on here. So most people, as part of your maintenance procedure, you need to take the intercell resistance of the battery. Okay, and when we say intercell, that does not mean the internal resistance of the battery. I'm not going to mention that today. We're talking about the resistance between this post here and this post here. So basically what we want to know is the resistance of the connection between these 2 jars. Okay, that is the intercell resistance, and that's a very important measurement to take, because if you have a high resistance connection between 2 batteries, then that's going to heat up, and it's going to cause losses, and it's going to cause your battery to not be able to give you the full power that you require. Okay, and the biggest mistake that we get is people don't quite understand what you're actually measuring. And what you're actually measuring, what you need to do is you need to put a probe on the actual lead post here and a probe on this lead post here. And you're actually measuring the connection resistance between this post and the bus bar, then the bus bar itself, and then through the bus bar, through the connection, back onto this post here. Okay. Now, as you can imagine, if somebody hadn't tightened down these bolts here and these were loose, you would have a loose or a high resistance connection between this point here and this point here. Okay, and we need to be able to find that when we're doing our maintenance. It sounds easy, but what tends to happen, and this is a very good example of what people do, is they use the clamps from the cell corder or whichever device that you are using, and they clamp like this. So the clamps are actually touching this bus bar here and this bus bar here. And then this clamp is touching this bus bar here and this bus bar there. So the only measurement that you are making is between this point here and this point here. You are not measuring the connection resistance here, and you can't see it because of the clamp here. You're not measuring the connection resistance there. All you're measuring is this little bit of, well, that piece of copper bus bar. And that's a useless measurement, an absolutely useless measurement. That's not going to tell you anything, because that copper bus bar is not going to degrade in any way, shape, or form. What will degrade, actually, let me go back. What will degrade is this connection here. Now, I've shown this arrow here. See this dark portion of the post? That's lead dioxide. And what's happened here, this C&D cell has a crack somewhere in the jar post seal, and it's allowing electrolyte to wick or seep up through the connection. It's not supposed to be able to do this. And when it does that on this is the positive post here, it's turning that lead into lead dioxide. It's kind of like a calcification layer. It's a very hard, lead dioxide is very, very hard. And what happens is if that creeps all the way up this post, it could, in theory, be behind this bus bar. So you have your lead plate, your lead post here, and then in between you have this lead dioxide layer, and then you have this strap. So what you need to be able to do is you need to be able to connect your device that's measuring the intercell resistance onto the post and only the post, and the post and only the post, and then you are measuring the whole connection resistance that way and the whole connection resistance that way. That is the only way that you are going to find a bad intercell, not internal cell, intercell resistance. So it drives me insane when I see people taking measurements and they put their clamps on like this. They do it all the time, all the time. If you put a clamp and it touches this bus bar in any way, shape, or form, the reading that you're getting is of no significance, so no significance whatsoever. Okay. Hopefully that explained that. And as you can see here, this is another example. This is the lead of the battery, okay? And then this is the bottom of the lug. So what we want to know is let's say this cable goes over to this point here. We need to be able to put our probe on the lead here. We cannot have it touching the lug here, because then it makes, once again, all you'll be measuring is the resistance of the cable. We need to measure from the lead and this connection resistance between the lead and the lug, and then over here between the lug and the lead. We need to make sure that that connection is good. And as you can see, that's very, very difficult on these 12-volt monoblock cells, because as you can imagine, your clamp kind of looks like that and looks like that. So if your clamp slips or touches the lug here, once again, the reading is completely irrelevant as soon as you touch that lug there. It means nothing, absolutely nothing, because the resistance of this cable is never going to change. It's a stranded cable. It's never going to change. We're not measuring the resistance of the cable. It's the intercell resistance between the post, the cable, back to the post again. Okay. And the last example you can see here, once again, this is the post. This is the strap. We need to measure between the post, the strap, back down to the post again. If our probe touches the strap, the measurement is irrelevant. Okay. Oh, there we go. Another myth: my battery voltage is 135 volts DC, therefore my battery must be good. This could not be further from the truth. Why my thing is doing this? Let me move on. Okay. And here's a good way to explain it. This is your house. Okay, so let's say you've got 120 volts coming in from your panel outside. And what we're going to say is that these are light fittings. Let's say they're in your kitchen. So you've got 3 lamps in your kitchen. Okay, and all 3 of them are lit. If you measured across each lamp, you would measure 120 volts AC because they're in parallel. Now, let's say we removed one of those lamps. Okay, so let's say you unscrewed one of the lamps. If you went to that lamp fitting and you measured between the live and the neutral of that lamp, you're still going to measure 120 volts. It's still going to be live. Just because the lamp is not there, you still have voltage available, okay? Because they're all in parallel. The same for a battery. Now we've got instead of having our 120 volts AC going to a house, we've got a charger coming in. And we have, let's say in this example, we have 3 strings of batteries, and they all measure 135 volts DC, exactly the same as the AC one, okay? Let's say we removed one battery completely. If we still measured the potential at the lugs going to the battery that we have lifted, we're still going to have 135 volts DC because they're in parallel, okay? So if we have one battery connected to a charger across the positive and negative, we're going to have 135 volts DC. But guess what? If you remove that battery and you still look at the termination points here, you're still going to measure 135 volts DC. So whether your battery is there or not, it's the charger voltage that you're reading when you measure 135 volts. It is not the battery voltage, okay? And this is explained here. Let's say you have an open cell in that battery. So let's say the battery is connected, but you have an open circuit cell in that battery. You will never find that if you think, oh, well, I'm just going to measure on the positive to the negative of this battery. I'm going to measure 135 volts DC. So that means the battery is good. Nonsense. If you turn that charger off, your battery is going to fail immediately because it has an open circuit. Cannot supply power if it has an open circuit. So reading a battery at 135 volts DC, all you are measuring is the charger voltage. It has nothing to do with the battery whatsoever. Oh, another popular myth. I have a ground fault on my battery. What I would recommend is you go and watch the video on our YouTube channel called Understanding DC System Design. Go to 44 minutes and 10 seconds. It goes into depth about how we measure ground faults on DC systems. But it's very, very rare that you're going to have a ground fault on your battery. And obviously the easiest way to do it, your ground fault detection system is either going to be on your DC panel or in your charger, okay? If you go and open your battery disconnect and the ground fault alarm clears, then that means, yes, the ground fault is on your battery. But if you open the battery disconnect and your ground fault remains on your charger or your DC panel, then it is not on the battery, okay? This portion here, ground faults are nearly always caused by load circuits, okay? Any fault on your load circuits will be indicated as a ground fault on the charger battery, and is near enough always a ground fault on the load. And this next slide basically shows you there's really only 2 things that can cause a ground fault on a battery. And that is electrolyte tracking from a battery to the rack. In other words, you need to have a physical crack in your battery, and the electrolyte has to leak from the battery, remain in contact with the battery, and touch the rack to get down to ground. Okay, so in truth, you should see, if you do have a battery leak, you should see the electrolyte level going down because that is a leak. And the other thing that can cause a ground fault is if the insulation on one of the battery cables has failed or is failing, and that cable is touching the rack, because the rack should be grounded. Okay, so that's really the only 2 things that can cause a battery ground. So it's very rare that either of those things are going to happen. So it's usually always your load circuits that cause ground faults. Okay, let me just do this one moment. I see some more questions in. I will get to them, I promise. Okay, maintenance mistakes. I have new batteries and the electrolyte level is at or below the low level line. Should I fill them before putting them on charge? And that is a big no. Do not fill batteries, new batteries, before putting them on charge. The gases produced by charging will do two things. It will displace the electrolyte and it will raise it to an acceptable level between the high and low level marks on the container. Okay, this is specifically from a battery manufacturer's manual. But when you start putting the battery on charge, it creates air bubbles that increases the level. And what it also does is that the lead inside a battery is spongy, and it does draw some of the sulfuric acid into the plates. So when you charge the plates, that sulfuric acid gets dispelled from the plate itself and increases the level of the electrolyte also. So do not add water or electrolyte to cells, particularly before your initial charge. Only adjust electrolyte levels when the cells are fully charged and stabilized at float voltage. Okay? So please bear that in mind. Oh boy. Oh, I am running out of time, and this is a good one. I need to keep the ripple current going to the battery below 5% of the C20 ampere hour rating of the battery. Okay? This is so common. And we'll go into why it's a little bit of a misconception. The first thing to note is that the charging system only creates ripple voltage, and that is an unavoidable outcome of bridge rectifier circuits or charger circuits. Okay, so this is the output of a charger, and as you can see, before it goes into a capacitor and an inductor, it is basically, we're just rectifying the AC, and there's gaps. This is actually DC. It's just called pulsating DC. And what we need is inductors and capacitors to fill in the gap between these pulses. Okay? But the thing is, it's impossible to fill the complete gap in. There is always going to be some ripple voltage left, even after we have inductive and capacitive filtering. So this is from the C&D manual, and this is an AC ripple voltage imposed on the DC charging voltage. And this is, it's saying 0.9% peak-to-peak AC ripple. So this isn't bad ripple. Now, the important thing to mention here is this is the open circuit voltage of the battery. And what that means is if you took the battery off charge, that is the voltage that the battery will sit at for a prolonged period of time until it starts self-discharging, okay? And the thing to remember is, as long as your ripple does not go below this value, then your battery will not be discharging. Between this point here and this point here, your battery isn't discharging, okay? It's only when you go below this open circuit voltage that you start discharging your battery. Okay, between this portion here and this portion here, that's only the difference between your charge voltage and your open circuit voltage. It's not discharging. Okay, so as you can see, this ripple here, the bottom ripple point there, is going nowhere near our open circuit voltage, so this is not a problem. But this is an example of 10 times the ripple voltage, so it's 9.9% peak to peak of the voltage of the cell. Now you can see, now remember we said that the equalized voltage of a battery is 2.33, so that would be roughly at this volt here. So when we start going above that, there's excessive gassing going on, and now you can see, look, we are going below the open circuit voltage rate. So now we are discharging this battery. So basically we are having micro discharges and charge cycles going on with a high AC ripple voltage of 9.9 volts peak, 9.9% peak to peak of the voltage of the cell. Okay, so hopefully that gives you an understanding of ripple voltage. This is not ripple current, this is ripple voltage. And hopefully we'll go on to explain this better for you. Battery manufacturers recommend that the RMS ripple voltage of the battery should be 0.5% of the DC voltage. So for a 135 volt system, it should be limited to 0.675 volts RMS. Now, the charger manufacturer has control over that by the design of the filter circuit. We can design a charger that meets that ripple requirement. All you need is more capacitance and more inductance for lower ripple voltages. Okay. Now, ripple current is purely a result of Ohm's law. I is equal to V divided by R. The charger manufacturer in many cases does not know what type of battery that's going to be connected to it. We just make the charger. All batteries have different internal resistances. All batteries. Okay. Even if you buy an Enesis 3cc battery, if you buy a 3cc5 and then a 3cc7, the two different batteries are going to have different internal resistances. And then, therefore, the higher the battery resistance, Ohm's law says, the lower the ripple current. And then the lower the battery resistance, the higher the ripple current. And the charger has no control over this whatsoever. The charger does not control ripple current, only ripple voltage. So here's a perfect example of how that affects your system. Okay, so let's say we have 5% ripple on this top battery here, the UPS 12-100. Okay, so we're saying that our charger, we're going to make sure that the ripple voltage out of our charger does not go past 0.675 volts RMS. So this is the important column here for this battery, and this is for the UPS 12. I think it's C and D that make these batteries. The internal resistance of this battery is 0.006 ohms, or 6 microohms. Okay, using Ohm's law, that would give us a ripple current of 1.875 amps. So we're meeting the requirements for our ripple voltage of being 5% ripple. But look, if we're trying to keep our ripple current at 5% of the C20 ampere hour rating of the battery, so if we go to that battery that has a C20 rating of 26, so 5% of that is 1.3 amps. So we are above, sorry, not a tick, we are above that 5% ripple voltage that everybody keeps saying, ripple current, sorry. We are above the allowed value. But if the same charger is then connected to this battery down here, okay, using the same ripple voltage, the same charger, we now have a different internal resistance. Now we have 1.2 microohms. So it's 1.2 microohms times 60, because there's 60 cells. The ripple current is now going to be 9.375 amps. But the 5% C20 rating of this battery is 9.95 amps. So we're actually below the 5% C20 ripple current allowed for that battery. So that is good. So hopefully that shows you for the charger that puts out the same ripple voltage, is completely dependent on what battery is connected to that charger to what ripple current will be. And that gets confused even more because there is an interesting paper from Emerson, and I've put the link in here, and hopefully I'll remember to put the link in the YouTube channel as well. The effects of AC ripple current on the life of a VRLA battery. And basically what they found is really the most important thing, if you look at this table, that you can put in 3 times the amount of ripple current and that results in less than a 3% impact on battery life. The temperature of the battery, which is what kills a valve regulated battery, does not really increase to a point that you have to reduce that ripple current. So I don't have enough time to go into this in depth, but it just shows you that there's a lot of inaccuracies in ripple current and ripple voltage measurements. If you need any advice, get in contact with us and we'll be happy to help you. Another battery myth is worst thing that you can do is overcharge a battery. Actually, the worst thing you can do is undercharge a battery. Prolonged undercharging causes excessive sulfation of the plates, and that is how you kill a lead acid battery, is sulfation of the plates. And it will eventually lead to irreversible loss of capacity because the sulfation turns into crystals, the crystals harden, and it stops the transfer of power between the positive and the negative plates. And if you leave it too long, those crystals are so hard that even an equalized charge won't get rid of them. Overcharging can slightly increase corrosion and lead to loss of water in the battery, but in a vented lead acid cell, that's not a concern because we can just top it up with water. In a valve regulated battery, it can cause the electrolyte inside the cell to dry out, which will eventually lead to battery failure, and it could cause the battery to go into thermal runaway. But I would say the worst thing you can do is undercharge a battery, because then if you do it for a prolonged amount of time, the battery is useless. Okay, I'm trying to get through this as quickly as possible. Another myth: if a vented lead acid cell has a crack in the jar and is leaking electrolyte, I can just keep topping it up with distilled water. It will be okay. No, because the water, normal water loss through charging is caused by the chemical process that changes the water back into hydrogen and oxygen, and then the gas is expelled through the flame arrestor. No acid is lost in that process in normal charging operation. It is only water. So you can top up with distilled water because the specific gravity of the cell isn't going to change. The acid is still in the cell. A leak causes loss of electrolyte solution that contains acid. So therefore, if you keep topping up with water when you have a leak, the solution will get diluted, the specific gravity will go down, and therefore that reduces the capacity of the battery. Oh, cool. Any questions? I was wondering how long we had to go. So I am now going to go back through the questions and see what we have. And you can still type in. I know we're over time, but I'm here until the last question is asked. So let's have a look. Based on my experience in practice, what is the max number of strings that can be put in parallel for an installation? Ooh, George, that's a good question. I don't think, in theory, there really is a limit. What you're going to struggle with is how you connect all of those parallel strings and allow the charge current and the discharge current to go through all those connectors and all those connection points. So that can cause difficulty. But in truth, in theory, there's no real maximum number of strings. But in practice, I haven't seen more than 5. Because in truth, there's so many different batteries that you can buy. There's really no reason to go past 5 parallel strings, because really the only reason you want to parallel is if the biggest battery that you can buy isn't big enough for your sizing needs, then you have to put another battery in parallel with it for capacity. But the other thing is redundancy. And really, all you need is 2 batteries for redundancy. You don't need any more than 2 for a redundant battery. So in truth, only if, I suppose, room size and that may change things a little bit. But if you can buy a big enough battery to only have 2 strings and you're looking for redundancy, I wouldn't go more than 2 strings, personally. Hopefully that answered your question, George. Somebody asked, in one photo, there was a battery bank in the same room as the switchgear. I know this is found in many places, but isn't recommended to have the batteries isolated in battery rooms? In other words, at what bank size would it be recommended to have a battery room? In truth, it's a very, very good question. The reason why you don't want to have batteries inside a room with the charger or any other piece of equipment is because if you use a vented lead acid battery, there is always going to be some gassing, and that gassing does contain hydrogen and oxygen, and that can cause not sulfation, what's the word I'm looking for, corrosion on some of the electronic components in other pieces of equipment. And the other thing is, obviously, hydrogen is flammable, it's ignitable, and if you put it in a room where there is the possibility of a spark, then you could, in theory, especially if the batteries are being overcharged, could in theory cause an explosive atmosphere. So that is why you really want to always have batteries in their own battery room with the correct ventilation. You can get around that by using valve regulated batteries, but you would have to look at the battery manufacturer's data sheet to see how much they gas and how much airflow is required for that room. Edmund's asked, is it possible to receive a copy of the slides? Unfortunately, Edmund, our slides are proprietary. You will not get a copy of the slides, but you can watch the video back and at any time. Another question, what material is recommended to use on the post to prevent corrosion? No-ox grease is what everybody recommends. It's designed for batteries. You only need a very, very thin layer for battery terminals, and in truth, you do have to keep your batteries maintained. You may have to reapply that grease at certain points and clean the posts, but no-ox grease is good. And actually, I think I read one of the battery manufacturers recently is recommending like semiconductor grease. Obviously, it has to be the non-insulating semiconductor grease because it gives you a better electrical connection. I can't remember why they said that. There was another reason why, but basically, you just follow. The manufacturer's manual has some fantastic information in there. I know that we're engineers, and I know most of us are men, and we don't like reading instruction manuals. I'm the same, but there is a huge amount of information in there that, and it will tell you what grease you can use on your post to prevent corrosion. How do you size batteries per battery duty cycle? David, thanks for answering that question that Norik asked. You do, what I would say is go to the, for example, Enesys, in their battery sizing calculator, you can put in duty cycles as part of your sizing program, and then the program will spit out the best battery for your application. But in this presentation, that is, like David said, a very, very complicated issue. And I would rely on your battery rep to do that for you. George asked, don't you include additional factors like temperature, aging into the battery sizing calculation? That's completely up to you. The aging factor is completely up to you. I know people who will put in a 0.8 aging factor because at 20 years, you're supposed to get 80% of the capacity out of the battery. So if I go back to the slide, remember I tried to keep things simple for this presentation, but if I go to the Enesys design sheet, there is a bit in there where you can put in sizing, aging and temperature if necessary. The only thing about this webinar jam is that I cannot go back and select a slide. I have to go back through each and every one of them until I get to the slide that I want. So yes, George, you are correct. Additional factors, here it is here. You can see that there is a design margin. Okay, so that is based on the engineer. You can say, I think they're going to add some loads to the system somewhere down the line, or you want some kind of margin added in there. You can add it in there, and then the aging factor can be added in there. So absolutely correct. There is no standard on that. IEEE does have some recommendations, but remember that IEEE is just recommendations. You have to decide that for yourself. And in truth, I would guess that your plant procedures should give you some kind of idea of what you should be doing. Hopefully that answered your question, George. Do you happen to know how often we should equalize batteries? Yes. And this is another misconception. Let's go back here. You only equalize your batteries when the cell voltage across each cell goes out with the recommended parameters of the battery manufacturer. So I'm trying to go back to the this one here. So if you had a C&D battery, and if it was calcium, it's saying that your cell voltage spread should be, if you set the voltage, let me explain this better. Okay, so it's saying that the voltage should be between 2.2 and 2.25 volts per cell. So that is 2.23 volts per cell times 60 is what you should set your charger at. So let me get my calculator out. 2.23 times 60 is equal to 133.8. So that is what you should set your charger at. But when you go and do your maintenance, you should be taking individual cell voltages. And if your cell voltage either drops below 2.2 volts per cell or goes above 2.25 volts per cell, that is when you need to do an equalize. Okay, if all of your cell voltages are between 2.2 and 2.25, you do not need to do an equalize, ever, except for when you're going to do a capacity test, because the battery manufacturer says you need to do an equalize before the capacity test. But in normal operation, as long as your cells are within the boundaries of what the battery manufacturer says, then you do not need to do an equalized charge. So when you say our batteries are only ever used once every 5 years during a load test, that's fine, Clint. You don't have to equalize them unless it goes out with that spread. Our battery-specific gravity seems to go up as they age. Is that normal? I would suggest not, Clint. The specific gravity should remain the same. Obviously, if you fill your batteries to the high level line and then you take a specific gravity reading, then your specific gravity is going to be slightly lower than if you take it to when the level is at the lower line, because obviously the water, the distilled water that you put in the cell does dilute the specific gravity to a point. But I have never heard of specific gravity going up as they age. There is a certain amount of acid in the cell that never leaves the cell, and as long as you keep them topped up to the same amount, I cannot comprehend why the specific gravity would go up. But you know what? I'm going to write that question down, and I'm going to ask our battery expert to see if he's ever heard of that. Okay, let's see this next one. We have multiple VLA in a stacked horizontal configuration, which means that the post and intercell connectors are quite close together. This makes it very hard to get the actual post to test correctly. Impossible. Have you come across any equipment or techniques which could help with this? Yes, Danny. There is if you're using a cell corder to take those measurements for the intercell, There is a specific clamp that you can buy from, I think it's Emerson now who owns Alba cell corders. There is a specific clamp that you can get for the button posts on the stackable VRLAs that is designed specifically for what you're trying to do. So go on their website, go on the cell corder website, and you'll be able to find those probes. I don't have time to look at it just now. If I have time, Danny, I'll have your email as part of this webinar. I'll go in behind and see if I can find it, send it over to you. How does short circuit affect battery life, and what to be tested after the incident? In truth, as long as you get the battery back on charge after a short circuit event, remember the only thing that kills a battery is being in a discharged state for a prolonged period of time. So if you have a short circuit event on the battery, as long as there is no physical evidence of any damage to the battery, then your battery in truth should be good. Check all the connections, check there hasn't been obviously there's a high current, so that high current had to flow through all of the connections and all of your cables, so make sure they're all okay. But in truth, the battery should be good to go, as long as it wasn't left in a discharge state for a long period of time. Another question. What is a typical life cycle expectation on a UPS system? That completely is down to the manufacturer of that UPS. Our UPSs are designed for a 20-year life cycle, because we oversize everything and we really build robust UPS systems. If you buy a commercial system, it could be between 5 and 8 years. And in truth, most manufacturers don't like to tell you how quickly you should replace your UPSs. So be very careful and ask those questions at the design stage. If you're going to buy a commercial type UPS, ask the manufacturer, how long should I expect to get out of my UPS? Another question, when should we consider temperature correction? My opinion is never. I know that's a very controversial statement. Your batteries should be in a temperature controlled environment. They're gassing, so you have to have a very good AC system to expel that gas and to keep your room in a good temperature. So as long as you set your room temperature at 77 degrees, you never need temperature compensation on a battery. Now, if your room isn't going to be in a temperature controlled environment, yes, I suppose temperature compensation is going to extend the life of your battery to a certain extent. And really all it's doing is changing for the seasons. When it gets hot in the summer, it's going to reduce the voltage, and when it gets cool in the winter, it's going to increase the voltage. But if you live in a temperate climate, let's say where the range of temperature is between 60 and 80 degrees Fahrenheit, temperature compensation isn't going to get you much, to be honest. That's within the boundaries of what the charger manufacturer says is okay to be charged. So, temperature compensation does bring in its own complications. If you can temperature control your room, then you don't need temperature compensation. If you can't temperature control your room, then consider temperature correction. Okay. Here's another question. For a 400 ampere hour battery, does battery breaker needs to be sized for 400 amps? No. You need to size your battery breaker for the short circuit capacity of the battery, or for the total current that you expect. Basically, you're just protecting the cables. So as a design engineer, you need to protect the cables. And so if you have a 400 ampere hour battery, but you have cables connected to it that will only accept 100 amps, you need to put a battery breaker on there that is going to break the current at 100 amps or whatever it would be to protect the cables. batteries will give you an enormous amount of power in short circuit. So it's really, in truth, that's a complicated issue that is out with this presentation. But it's not as simple as a 400 ampere hour battery should have a 400 amp battery breaker. For equalizing in vented lead acid cells, what about mitigating acid stratification? That's a good question, David. Battery manufacturers don't recommend that you equalize the batteries for acid stratification. They only recommend equalizing the battery for cells being out with their tolerance. IEEE may have some wording in there for acid stratification. Once again, that's just a recommendation. Equalizing your battery is not going to do any harm to your battery. Okay, for a vented lead acid cell, the only thing it's going to do is boil off a little bit more water, and you're going to have to top it up a bit more often. It can, in theory, if you did it every week, you're going to be overcharging the battery, so it could cause minor corrosion on the plates, but it's not going to be excessive. Okay. Once again, David, I'll ask my battery expert about mitigating acid stratification. And if anybody doesn't know, acid stratification is if obviously acid is heavier than water. So in truth, the acid could sink to the bottom. So the top part of the electrolyte could be lesser specific gravity than the bottom part, which would give uneven discharge and charging across the plates. So it is a good question, but I've never heard of a manufacturer recommending it. So great question. I'll see if I can get back to that. Clint's asking, how long should we equalize the string for? Ooh, another great question, and it's very complicated, but if you follow the manufacturer's guidelines, what you're supposed to do is you put your charger on equalize and you monitor the current, okay, with an amp clamp. And then once the current going to your battery has not changed for, I think it's a 3-hour period, but you'd have to read the manufacturer's guidelines on this. Basically it's called current stabilization. Once the current into the battery has stabilized for a prolonged period of time, that is when your equalized time starts. And then every manufacturer has a different amount of time that they recommend their cells to be equalized for. A general rule is 72 hours. And once again, if you do it for longer on a vented cell, all it is going to do is boil off more water. It's really not going to affect the cell too much. But you do have to wait until you get to current stabilization before you start the equalized timer. So if the manufacturer's manual says that you should equalize the battery for 72 hours, that is 72 hours after you get to current stabilization. And if you have a huge battery, it could take up to 24 hours to get to current stabilization. So that means you would need to perform the equalize actually for 92 hours. For VRLE batteries, if a battery fails, do all top batteries in the stack to be opened, or can we just replace only the failed one without dismantling the other cells? If it is in the stackable type, then you can replace. If you can actually physically replace a battery, if it fails, then it's okay to do that, whether it's a jar, whether it's a single, a jar with 1 cell or a jar with 6 cells. It doesn't matter. As long as you can actually physically replace it, you can do it. But I would warn against it. Usually if one battery has failed, that's an indication that something is going on. And as with anything, every battery manufacturer is exactly the same. The only thing that will give you is a good test of your battery is a capacity test. You can do a cell quarter test. You can do internal resistance, intercell resistance. You can do all these things. Everything only says, I think you have a problem with your battery, you need to do a capacity test. So if a cell failed or a battery failed, I would say replace that battery and then do a capacity test to make sure that all the other batteries and cells are good. Would you please help by informing the specific test probes to measure the intercell resistance? What I would say is yes, I will do what I can. I'll see if I can find those probes for you. I can at least find the data sheet for it. Wow, 30 minutes over time. I knew the battery one was going to get a lot of questions. So for those people who stayed on until the end, thank you very, very much for listening to me for that amount of time. Goodness me, well done. Once again, we will be putting this presentation up on our YouTube channel, and I'm sure that our marketing department are about to put the link, oh, Taylor, you are amazing, into the comment section there. So there is the link to our YouTube channel. All of the previous presentations that we've done are on our YouTube channel. You can go and look at them. And if you have any other questions or concerns, you can click on the other link that Taylor just put into the chat bar, which takes you to our website. Or you can email us at sci.marketing@ametek.com. And don't forget that we have a fantastic battery training class. It's a 2-day class. It's part of our UPS training. It's taught by Bob Leslie from ATS. He's a contractor that we use. He is fantastic. It is the best 2 days you can spend on batteries. He's informative. He keeps it light. It's just really, really good. I'm not just saying that because I want you to sign up for the course. I promise you. He is the best trainer that I've ever seen on stationary batteries. So if you're interested in learning more in-depth stuff that I haven't gone over, then sign up for our battery training. So you've got all that information at your hands. Feel free to contact us. We're here to try and help you as much as we possibly can. I've seen some of the comments come in here. I'm glad that you enjoyed it. Once again, I'm not a battery expert, but hopefully I gave you some information that helped you in either your maintenance or the choosing of certain batteries for your system. So I appreciate the great comments. Don't forget to fill in the survey that we send out, because the reason I did this was because we got so many surveys that came back that says, I would like to have more information on batteries. So that's why I did this class. So if you have something specific you want us to discuss at our next webinar, put it in the survey. I read every single one of them, and I will try and create a class for that. So until next time, I am going to stop waffling on and let you get back to work. Thank you so much for taking time out of your day and listening to me. I know your time is precious, and for you to take an hour and a half out of your day to listen to me, I really, truly appreciate that. Have a great week, and I will talk to you next time. Thanks very much, everyone.